The fuel system is designed to provide fuel to both engines and the APU. The fuel system consists of three subsystems. The storage subsystem, which includes vented integral fuel tanks in the aircraft wings. The distribution subsystem, which permits operations like engine feeding, APU feeding, tank refueling and defueling. And finally, the fuel indicating subsystem, which provides indications and failure information to the crew and maintenance personnel. Fuel is carried in two integral wing tanks. The aircraft fuel capacity is 13,120 kilograms, 28,924.1 pounds, or 6,560 kilograms, 14,462.05 pounds per tank. During normal operation, each wing tank supplies fuel to one engine through a collector tank located at the inboard end of each tank. The APU is supplied with fuel from the right-hand side collector tank. The engines are fed by means of primary ejector pumps, which are driven by high-pressure motive fuel flow supplied by the dedicated engine fuel pumps. The APU is fed by means of electrical pumps when the engines are not running, or by means of the primary ejector pumps with the engines running. The backup electrical pumps in each collector tank ensure engine feed in the event of a primary ejector pump failure and also provide a source of pressurized fuel supply to the engines and APU for ground and in-flight start. The aircraft can be pressure refueled and defueled at the right-hand wing leading edge by means of a standard single-point refueling adapter and the associated fueled panel. Additionally, the aircraft may be refueled using the gravity refuel ports located on top of the wings. The fuel gauging system provides a highly accurate measure of the fuel in the wing tanks, as well as fuel low level and temperature indication for display on the ICUS and MFD. Fuel system operation is designed to provide a continuous supply of pressurized fuel to the engines without pilot intervention. However, the fuel control panel located in the cockpit allows the pilot to manually control the electrical fuel pumps to supply both engines and APU from one tank by using the crossfeed function. The aircraft has two structurally integral wing tanks. Each wing contains a surge tank to collect fuel during wing down or uncoordinated maneuvers, and a collector tank to ensure continuous fuel feed to the engine throughout the whole flight envelope. The arrangement of the tanks permits the fuel to flow from the outer tank area to the wing root and into the collector tank. Each tank contains baffle and flapper check valves that prevent fuel from escaping from the collector tank and prevents fuel from entering the surge tank. The tank vent system is designed to keep the pressure differential between the tank and ambient within structural limits under all operating conditions, and to prevent fuel spillage during flight maneuvers and hard braking. Each fuel tank is vented through two independent lines into a surge tank located in the outboard section of the wing. Due to gravity, water inside the fuel tanks will collect at two locations in each wing. Two drain valves drain the water of the collector tank. The aircraft fuel distribution system has three subsystems: engine feed, APU feed, and refuel-defuel. The engine feed system ensures a continuous supply of pressurized fuel to the engine during aircraft operation by using ejector and electrical pumps. It also has a cross-feed feature that allows fuel supply to both engines from either one of the wing fuel tanks. The APU fuel feed system ensures a continuous supply of pressurized fuel to the APU. Refueling and defueling use the same adapter in the fuel panel, and gravity refuel uses two overwing refuel ports, one for each wing tank. The fuel feed system has one main engine feed ejector pump and one AC electrical pump for each wing. The primary fuel pump is an ejector pump, operated from motive flow supplied by the engine-driven fuel pump. In the event of failure of the main engine feed ejector pump, the AC boost pump provides backup fuel flow to the engine. AC Bus 1 powers the left AC fuel pump, and AC Essential Bus powers the right-hand AC fuel pump. In case of an electrical emergency, the right-hand AC fuel pump will be supplied from the ram air turbine. A DC-powered electrical centrifugal pump located in the right-hand collector tank provides a source of pressurized fuel supply for APU and engine start in flight, or on the ground if the engine feed ejector pump and AC power or the AC fuel pump are not available. Electrical power will be supplied from the DC Essential Bus 2. A 3-position rotary selector knob on the cockpit fuel control panel controls each of the electrical pumps. With the knob set to off, the corresponding pump will not be powered. When the knob is placed in the auto position, the SPDA determines when the pump should be powered. When the knob is placed in the on position, the corresponding pump will be powered continuously. When the AC fuel pump selector knobs are in the auto position, which is the normal position, the detection of an ejector pump failure will result in automatic start of the AC fuel pump. Pressure switches, one for each pump, monitor the output of the electrical pumps. MAU-1 monitors the status of the AC fuel pump 1 pressure switch, and MAU-3 monitors the status of the AC fuel pump 2 and the DC fuel pump pressure switches. Each MAU transmits the data on the ASCB for ICAS display and control functions. The ICAS messages fuel AC pump. For APU start, the DC and AC fuel pump switches have to be in auto position. If you select APU start, the DC fuel pump will start to supply pressurized fuel. As soon as AC power is available, the AC fuel pump will take over. When the engine is running and the engine feed system is operating, fuel will be supplied from the ejector pump to the engine as well as to the APU. If necessary, the APU can be supplied with fuel from the left-hand tank by moving the cross-feed switch to low 2, and with AC power available, the left AC fuel pump will supply pressurized fuel to the APU. If the left engine is operating, the left ejector pump will also supply the fuel to the APU. Standard refueling and defueling is performed by use of the single-point pressure refueling-defueling port. The port, along with the fuel panel, is installed behind an access door on the right-hand leading edge, outboard of the wing-mounted engine. If the pressure refueling system is inoperative or no pressure refueling is available, the aircraft can be refueled by gravity through the 2 overwing gravity refuel ports. Before beginning refueling and defueling, the aircraft must be grounded. For pressure refueling, the truck shall be grounded to the aircraft through the right landing gear. For gravity refueling, besides the truck aircraft grounding, the fueling nozzle shall be grounded through grounding points below the wings. Power selection. The normal and battery positions control the power source for the refuel system. In normal position, DC buses 1 and 2 provide power to the refuel control solenoids and the FCU. In battery position, the system is powered by Hot Bus 2. This allows fueling with the APU not running and no external power connected. Refueling. The open and closed positions control both of the refuel shutoff valves. With the switch in the closed position, the valves are commanded closed in both the manual and the auto mode. Selecting the switch to the open position in auto mode causes the FCU to take control of the refuel shutoff valve via the refuel control solenoid. The FCU will close the valves to stop refueling when the pre-selected quantity is reached. In the manual mode, the valve is controlled directly by the switch position, removing the FCU from the control loop. Refueling has to be stopped manually by selecting the switch to the closed position or stopping the external fuel supply. Defueling. The open and closed positions are available on the defuel shutoff valve. With the switch in the closed position, the valve will be commanded closed. To start defueling, the switch has to be moved to the open position. Each switch on the panel is guarded to ensure all switches are in the closed or normal position when the access door is closed. The following indicator lights are provided on the fuel panel: left-hand tank and right-hand tank. The closed light will be illuminated to indicate the refuel shutoff valve for the respective tank is closed. Defueling. The open light will be illuminated to indicate the defuel shutoff valve is open. The refuel-defuel indicator has a 2-line, 8-character display which displays the fuel quantity on the upper display and the pre-selected quantity on the lower display during automatic refuel. The indicator includes 2 3-position toggle switches. When in the increase position, the pre-select quantity shown on the indicator lower line will increase. Likewise, when in the decrease position, the pre-select quantity will decrease. The top line of the indicator normally displays the current total fuel quantity in both tanks. When moved to the tank select position, the display will alternate from total tank quantity to left quantity to right quantity. Moving this switch to the test position will initiate self-test of the fuel quantity indicating subsystem. In case of a failure, fail will be indicated. The aircraft tanks can be defueled through the single-point refuel adapter by suction, applying suction by ground equipment, or by pressure defueling using the electrical fuel pumps of the aircraft. Both defueling techniques can also be used together. To pressure defuel the aircraft must be energized by starting the APU or by connecting external AC power. To begin this procedure, first ensure that the aircraft is properly grounded. After connecting the nozzle to the refuel adapter, select the defueling switch to the open position. Verify that the open light is illuminated by making sure that the defuel valve open advisory message appears on the ICUS. In the cockpit, select AC fuel pump 1 and 2 selector knobs to the on positions. Select the crossfeed selector knob to the low 1 or low 2 position. When the desired fuel quantity is reached, stop defueling by switching the AC fuel pump 1 and 2 and the crossfeed selector knobs to off. At the fuel panel, select the defueling switch to the closed position. Verify the open light is not illuminated. The fuel nozzle can now be removed. The suction defuel operation is performed similarly to the pressure defuel procedure. Ensure the aircraft is properly grounded. After connecting the nozzle to the refuel adapter, select the defueling switch to the open position. Verify that the open light is illuminated. In the cockpit, select the crossfeed selector knob to the low 1 or low 2 position. When the desired fuel quantity is reached, stop defueling by selecting the defueling switch on the fuel panel to the closed position. Select the crossfeed selector knob in the cockpit to off. Verify the open light is not illuminated. The fuel nozzle can now be removed. The fuel system indication system consists of the following elements: electrical fuel quantity, mechanical fuel quantity, fuel temperature, and low-level indication, which is a dedicated probe that is independent from the fuel quantity indication probe. The primary means of determining fuel quantity is an AC capacitance-type electrical fuel indicating subsystem. If the electrical fuel indicating subsystem should fail, a backup mechanical quantity indicating subsystem, which operates by means of magnetic level indicators, allows the aircraft to be dispatched. The left and right fuel quantities can be monitored on the ICUS. The fuel system synoptic page can be selected on the MFD by selecting Systems and then Fuel. Total fuel quantity and fuel used are displayed as digital values. In addition to digital values, the left and right tank quantities are shown on an analog scale. The fuel temperature in the left-hand tank is displayed in green as long as the temperature is above -37 degrees Celsius. Below that, it appears in amber and amber dashes if there is a fault. The status of the main ejector and electrical pumps is indicated in white as long as they are in standby, turn green when in operation, and amber dashes if there is a fault. A fuel temperature sensor is installed in the left tank only. If the temperature in the left tank drops below a predetermined value, a fuel tank low temp caution appears on the ICUS. The fuel temperature can be monitored on the fuel system synoptic page. In case the fuel level in the associated tank falls below 400 kilograms, 880 pounds, a low-level warning will be provided to the crew. In case of loss of the transfer flow from the scavenge pumps, for example after an engine failure or loss of motive system, the fuel contained in the collector box will flow out to the stub so that the fuel inside the collector box and the fuel inside the rest of stub tank would reach the same level. With up to 1,800 kilograms, 3,970 pounds of fuel inside that tank, it is then possible that the level equivalent to the low-level warning activation point could be reached as the fuel level inside the collector box decreases and the fuel 1 or 2 low-level warning ICUS message would be displayed, even though the fuel quantity indication on ICUS or the MFD fuel system page displays up to 1,800 kilograms, 3,970 pounds in that tank. Note: in case of loss of the transfer system followed by the ICUS warning message, fuel quantity indication monitoring during the flight is achieved through the ICUS or MFD fuel system synoptic page. Engine flameout due to fuel starvation may occur if the airplane is submitted to attitudes greater than 15 degrees nose up or down, uncoordinated maneuvers, or negative Gs. The mechanical fuel indicating system is a completely independent system used to provide an auxiliary visual display of the fuel quantity by means of 3 magnetic level indicators or dripsticks per wing. The magnetic level indicators are mounted into fuel tank access panels in the wing. To measure the fuel quantity with the magnetic level indicators, rotate and lower the indicator. The float magnet will keep the rod magnet, and the height of the fuel level is displayed on the stick. The weight of the fuel on board can then be determined by referring to the chart in the operations manual.